Okay, good afternoon, everyone. I'm Pascal Pradeshanan from CMHL from Shanghai Jiaotong University. So today I'm going to talk about optimizing DTMB, how resistance with a multi-objective approach we're utilizing freeform deformation volume match. So I have 5 contents to talk about, and let's start with the background. So for the optimization with the surrogate model, the first thing is we need to prepare the data for modeling. So we need to prepare discrete data like design variable and then mapping with the result for this study. The function of the design variable uh, is the resistance. So we mapping the desirable with the resistance, and then we try to uh, dis distribute all data um, in the plan. And after that, we estimate the parameter and training. And the final approach is testing the model of the surrogate. So for the conventional how form optimization approach using the surrogate model, the mesh is generated consecutively. That means each observation we need to generate mesh individually. So this is one of the time-consuming and costly tasks. So for example, if we have 100 observation, so we need to generate mesh 100 times. So we propose the method about mesh deformation for surrogate modelings. So this method is deform the mesh directly. Like we can only generate mesh only first time, and then we use deformation method in order to deform mesh directly. So it will help us to decrease the time for generating mesh. And about the freeform deformation. So the freeform deformation is a deformation method that we will use in this study. So let me introduce about this method. And this method is proposed by Siderberg and Perry in 1986. So the technique initiated by establish a local coordinate system first, and every x defined by coordinate as this equation, and so the location of control points are defined as P. And after that, the deformed position will be evaluate the vector trivial Bernstein polynomial by the following equations. So about the volumetric deformation solver, we also use this freeform deformation to this solver. So this solver, including the computational domain mesh information reading and FFVD module and computational domain mesh deformation module, mesh iterative optimization module, and computational domain mesh output module. So the solver procedure is the first one is we need to read the coordinate and topology information of the structure boundary mesh. And after that, we utilizing dynamic mesh technique. So the coordinate and of the structure boundary mesh are reset. And the reset after that, for the freeform deformation module input, the reset structure boundary mesh point are input into this module. And within this module, the coordinate of the structure boundary mesh points inside the lattice are computed based on the structure boundary mesh points and lattice position information. And after that, we calculate the deformation. So the coordinate of the deformed structure boundary mesh point are determined from the movable control points and their displacement distance based on this freeform deformation formulas. So the displacement and direction of each grid point on the structure boundary are obtained through the interpolation. So after that, we update the mesh. Both structure boundary and computational domain mesh are updated according to this formula, and where the gamma C represent the mesh deformation diffusion coefficient and the VC represent the deformation vector fields. So about the multi-objective how optimization of this DTMB. First, let me introduce the optimization process. So first we have the initial model. So the study is a DTMB, and after that we create a design of experiment. Yeah, we distribute the design variable into the plan, and after that we generate mesh deformation. And after we get the mesh, all of the mesh deformation, we predict the hydrodynamic performance in this study. So we use resistance as the hydrodynamic performance. So after we get the resistance from all of this mesh design variable, then we can use this data to building a surrogate. And after we building a surrogate, we can find the global minimum point by using the optimization algorithm to search the global optimum points. So in this study, we use stochastic searching, such as NSGA2, in order to search for the global minimum. And after we got the optimum solution. So after we get the optimum solution, we verify with the high fidelity result, like a CFD, in order to validate the result. So the initial model, we used DTMB 5415 with this geometrical characteristic. So this model is tested in Insian model 2340. So it has a length at borderline about 5.72 and breadth of 0.76 meters, draft at 0.76, and this DTMB will be evaluate the performance for two foot numbers. The first foot number is 0.2 and another foot number is 0.24. And for simulate the result, we use our in-house NAOE form SJTU in order to predict the resistance. And after that, we place the freeform deformation lattice onto the bulbous bound of the DTMB mesh volume. After we get the volume mesh of the DTMB, we place the lattice, deformation lattice onto the bulbous bound, and then we deform the mesh directly into. For this study, we deform into 20 samples in search direction and in sway direction. So as you can see, the left picture is the red points denotes the movable points that deform into the search direction, and for the right picture denote the red point denote movable points that deform the bulbous bulb in sway direction. So for the optimization function, we constrain the sway and the search direction between minus 0.02 to minus 0.02 to 0.02, and we also constrain the relative volume and the relative weighted surface area within minus 1% to 1%, and within minus 1.5% to 1.5% respectively. So after that, the local coordinate control points and design variables were configured into the FFD or para.dat file, which will be used to calculate in the module that we present. So mesh deformation for the sampling plan. For about the mesh deformation, I used the optimal Latin hypercube in order to stratify the sample evenly into the domain, and we deform the mesh in accordance with this stratification. So after that, as you can see that after we constructing a surrogate model, we can see that 20 sampling points can create a reliable surrogate model. And so we use this 20 sample points in order to optimize this Howe form. And after that, we use critic model in order to construct a surrogate. And after we can see this critic model, we can see that the optimum point placed at the edge or the constraint of the plane. So after we get the optimum point, we also use that optimum point to validate with the CFD data. So as you can see, at root number equal to 0.2, we found that the dynamic pressure in front of the bulbous bulb for the optimized Howe is less than the initial Howe. And also in the root number equal to the 0.24, the optimized Howe have less dynamic pressure area than the initial Howe. Yeah. So about the wave pattern, we can see that the transverse wave pattern also less for the optimized result less than the initial Howe form for both root number. So the viscous resistance, which based on the dynamic pressure, also reduce only in the root number equal to 0.2 is reduced about 0.25%, and and for the root number equal to 0.24 is reduced around 0.27%, and the wave resistance. So in this context is about we can reduce the wave pattern, and the wave pattern is also the part of the wave resistance. So as you can see, the wave resistance also reduced more than 14% for the root number of 0.2 and 9.8% for the root number of 0.24. So that's influence the total resistance to reduce around 3% for both root numbers. So for the conclusion, So the volume mesh deformation solver introduced in this paper adeptly deform volume mesh structure concurrently, and this solver facilitates efficient Hall optimization through the proposed module. Yep. Thank you.
Did you have any problems with free-form deformation parametrization or optimization? Okay, so on page 16,
Okay.
I think you show the motion of the points.
Page 16.
Okay, so you see what you have here is 7 points, and you only move the middle one, but you don't move the 3 on the left side. Okay, so when you run optimization here, you only have 1 degree of freedom, right?
Yes, because of the no, in this study we have two design variable.
You have this side
Yes, and this side. So we are deform in these two direction. For the we don't encounter any crucial problem, but the crucial problem is only we deform it too much. That will create the mesh to be too sharp, and yes, that will be lead to a big problem. So, but in this study, we constrain the deformation to only 0.02, so there is no problem in this study.
Thank you very much.
You're welcome.